Module 3.2, Differentiation and the Slopes of Tangent Lines. Objective 1, calculate and understand the notation of differentiation. Objective 2, understand and construct tangent lines and their slopes and the functions. Objective 1, calculate and understand the notation of differentiation. There are many different common uses for differentiation. To differentiate or to find a derivative is used in business to find the activity of a stock, in physics to calculate the motion of an object, in medicine to find the effectiveness of a drug, and the list is endless. Unfortunately, there are several notations for finding a derivative. There's the derivative of y in terms of x. We can write also, we can write it d sub x. And another way I've seen it is the function prime of x. The formula for finding the derivative, let's use the function prime of x for this time, is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. In example 1, we need to find f prime of x, or the derivative of the function, if f of x is equal to 2 minus 3x. So let's take a look at this one. We want to go using the formula, the limit as h approaches 0 of 2 minus 3, and we're going to substitute the x plus h in for x, minus the function itself, over h. Second step, we'll do full on the x plus h quantity squared. Alright, in our next step, let's distribute the 3 in. We need to be careful to watch our signs. Okay, and in this step, I think we can cancel the 3x's. We can cancel the positive 2 and the negative 2. So that's going to give us that's 3h squared all over h. We can factor out the h in the numerator. Notice that our h's cancel, which is good news. And now if we take the limit as h approaches 0 of negative 6x minus 3h, if h is 0, that means this is going to leave us, because negative 3 times 0 is 0. That's going to give us minus 6x. And we have now found the derivative. All right, in example 2, we're going to take the derivative of r in terms of x. So once again, let's take the limit as h approaches 0, and we're going to do 4 over, this time we're going to put x plus h in the place of x, minus the function itself, all over h. Step 2, that's going to be the limit as h approaches 0, and we need to give this left one here an x. So it'll be 4x over x times x plus h. And we need to give the one on the right, this one here, an x plus h. So it'll be 4 plus h over x times x plus h. So notice I gave it an x plus h here and an x here. So now that they match, limit as h approaches 0 of 4x minus 4x minus 4h. Be careful with my signs. Over the denominator over h. Okay, now as h approaches 0, notice that the two 4x's in the numerator will cancel, which will give us minus 4h over x times x plus h over h. And we can go ahead and sling a 1 under that, right? Because it's a denominator of 1. So that will give me limit as h approaches 0, negative 4h over x times x plus h times, because I'm going to invert this and multiply instead of divide. Okay, and here we have our h's that will limit as h approaches 0. And our h's will cancel, so that'll give me minus 4 over x times x plus h. And as h goes to 0, that'll give me minus 4 over x times x, which would be x squared. And we have now found the derivative for example 2. Alright, looking at example 3, we're given that g of x is equal to the square root of x minus 5, and we need to find the following. Okay, let's go through and do my definition. We know that our definition is equal to the limit as h approaches 0, and we're going to substitute x plus h in there, minus 5, minus the function itself, over h. Now here, I don't know if you can remember, to get rid of square roots, we learned in algebra that we can multiply by the conjugate. So if that's a minus, we're going to multiply by exactly the same thing, except it's going to be a plus. So we'll just make it x plus h minus 5, and instead of minus, we're going to put plus. Square root of x minus 5 all over, and we're going to do the same thing on the bottom to make it legal, so that we're multiplying by 1. Anything over itself is automatically equal to 1. Okay, and then when I multiply, a neat thing happens in the top. You know, we multiply the two, we're going to do FOIL, but the middle two will cancel each other out. So what we're going to end up with is the limit as h approaches 0 of my numerator, which will be x plus h minus 5 minus parenthesis x minus 5 all over, and then we have in the denominator we have the h from the original one, and then we have the square root of x plus h minus 5 plus the square root of x minus 5. Okay, and this will give me the limit as h approaches 0 of, and I'm going to do the distributive property with the minus sign, so that's going to give me x plus h minus 5 minus x plus 5. Have to be careful with those signs. All over h times the square root of x plus h minus 5 plus the square root of x minus 5. There we go. Okay, parentheses closed. Notice that the 5's will cancel. Notice that the minus x and the positive x will cancel, which will give me the limit as h approaches 0 of h on the top is the only thing that's left over h times these square roots that are on the bottom. Make sure my square root goes all the way across there. Close my parentheses, and notice that these h's will cancel. So we're given with 1 on top and these two things on the bottom. Well, if I let h equal 0, that means that that's going to give you an x minus 5. And so you're going to end up with 1 over the square root of x minus 5 plus the square root of x minus 5. And so there's two of them, right? So that would be equal to 1 over 2 times the square root of x minus 5. And that is the derivative. Okay, and in part B, they're asking for g of 7. So all we got to do is just plug 7 into g. So that's going to be equal to the square root of 7 minus 5, which would be equal to the square root of 2. And then they're going to ask me for g prime of 7. So if I put 7 in there, it would be equal to, now remember, 1 over 2 times the square root of 7 minus 5, which would be equal to 1 over 2 square roots of 2. And then if we wanted to make sure the square root's off the bottom, we're going to multiply by square root of 2 over square root of 2, which would be equal to the square root of 2 over, and then square root of 2 times 2 would be 2, and 2 times 2 is 4. And then that would be g prime of 7. In order for a function to have a derivative at a particular point, the function must be continuous at that point. Remember that continuity is defined as the limit existing from both the left and right hand side, that the function exists at that point, and that they all three give the same height. We also need to watch for two exceptions, which include the vertical tangent line and a sharp corner. A vertical tangent line gives us an undefined slope, and a sharp corner has more than one tangent line. Let us look at a function and determine the intervals in which it will have a derivative and the points in which it will not. It's going to have a derivative everywhere from -6 to -2, not including -6 and -2, because -2 has a sharp corner, therefore many tangent lines can be drawn there. And obviously -6 is an endpoint, and so you can have infinite number of tangent lines there. Okay, notice that also areas in which we can have a derivative are from -2 to 0, not including -2 and 0, because at 0 we have a limit, but the functional value is not the same as the limit. So notice the functional value is 0, whereas the limit as it approaches from this side and from the left-hand side are going to give you 4. Okay, and then we have another area in which we'll have a derivative, and that is going to be from 0 to 2, not including 0 or 2 again, because obviously 0 we talked about just a second ago, and 2 you've got a open endpoint there, and so infinite number of tangents can be drawn. And the last little area is between 2 and 3. And between 2 and 3, not including 2 and 3, because both 2 and 3 are endpoints, and so infinite number of tangent lines. So this is the areas, these open intervals combined are going to be the areas in which you can have a derivative. So you cannot have a derivative. Let's write this up here. So we cannot have a derivative at -6, -2, 0, 2, 3. And so these are the areas where you can have a derivative, and here are the areas that you cannot. Okay. In the previous section, we described the height of a golf ball by h of t is equal to -16t squared plus 64t, where t was the time in seconds and h of t was the height of the ball in feet. For this example's sake, let's pretend that the ball went straight up and then straight down. Then what would the derivative h prime of t, or the change in height, represent? What would the h double prime, or the double derivative, represent? Well, the first derivative is going to represent the change in height. And what would the change of height be called? We would either call it speed or velocity. So let's use speed for here. And then we would take that and take the derivative of that would give us h double prime. and that would be the change in speed. And we would call that acceleration. Understand and construct tangent lines and their slopes and the functions. First, let us make sure that we understand slopes of lines. Now, if a line from left to right heads downward like this, let's call this f of x, then this would be a negative slope. If the line goes upward from left to right, we'll call this g of x, then this would be a positive slope. If a line stays flat like this, this would be slope is 0. And if a line was vertical like this, then this slope would be undefined. Alright, second, we need to make sure that we understand tangent lines. So let's take a function like this. And let's take a look at slopes. So notice at right here, we would have a slope that would be equal to 0, right? So my slope here would be equal to 0. And my slope here would be equal to 0. So notice something that's going to be very nice for us to know. Notice that our slopes are equal to 0 when this thing is going from moving up to the top of the hill and then coming back down. We notice that slopes are 0, and we'll study more on this later. Notice that here, if we draw a tangent line, that slope would be negative. If we draw a slope here, this slope would be positive. Alright, so we've got 0, positive, and negative slope lines. Okay, we're going to let f of x is equal to negative x squared plus 2. The first thing we need to do is we're going to graph f of x. So let's see. Using our functional notation or graphing utility, we can kind of tell that this is going to be a parabola upside down because of the negative. Alright, the second thing that they're going to ask us is to draw a tangent line at x equal 1. So right here, we'll draw a tangent line. Okay. It says now use the limit definition to find the derivative of f prime of x. Well, if you'll remember that our formula for that is the limit as h approaches 0 of negative x plus h quantity squared plus 2 minus negative x squared plus 2 all over h. That'll give me the limit as h approaches 0. I'm going to do full again, so that'll be x squared plus 2xh plus h squared plus 2 plus x squared minus 2 all over h. Right, distribute the minus, so that would be the limit as h approaches 0, negative x squared minus 2xh minus h squared plus 2 plus x squared minus 2 over h. And that'll give us the limit as h approaches 0. And notice my x squares will cancel. Notice that my 2's will cancel. And that'll leave me with minus 2xh minus h squared over h. I can factor out my h. It'll give me negative 2x minus the h over h and the h's will cancel. And at that point in time, I can take the h approaches 0 because we're dealing with a polynomial, and notice the h will go. So that'll leave me with negative 2x. Okay, so that is the f prime of x, or the derivative of x. And then if I plug 1 into that, that would be, so f prime of 1 would be equal to negative 2 times 1. It would be this with 1 placed in it, which would be equal to negative 2. And so you can see that the slope, even though my drawing is not the prettiest in the world, we can see that the slope for this is going to be close to negative 2. And in calculus, it's actually negative 2.